Hello everyone, welcome back to the lecture series of learning theory of automata and formal languages. My name is Binayak Parashar. I am working as an assistant professor in the Department of Computer Science and Engineering at Ajay Kumar Garg Engineering College, Ghaziabad. So, we are continuing with unit number 2 and we have completed almost 4 to 5 topics regarding the topic which is known as regular expression. So, in the regular expression context, we have tried to understand what is the meaning of this expression, what is this particularly used as a, why this is particularly used as a representative for a regular languages, and it becomes very easy for understanding a regular expression, so that we can convert any expression to finite automata or finite automata to regular expression. So, in the previous video we have understood the concept of how to convert a finite automata to regular expression by using a particular theorem which is known as ARDEN'S theorem. Okay. But we have tried to understand the simplification process of using ARDEN'S theorem, but here in this particular video we will try to look into some of the basic identities, okay, that is being used in order to accumulate this concept. Okay. Now, let me check it out what is the agenda for today's video. This video will comprise of some of the algebraic method used in ARDEN'S theorem, and also we will check some of the basic identities. So, let me go back to the first slide. The first slide, again I am going back a little bit of revision with ARDEN'S theorem, what ARDEN'S theorem is all about. If anyone has skipped this particular context, then you can get back to the previous video. So, ARDEN'S theorem, what it says is that ARDEN'S theorem says that if for two expressions, say suppose P and Q, okay, are two regular expressions over any input alphabet, and if P does not contain epsilon, okay, then the following equation, which is in the form of R is equals to Q plus R P, that is R is equals to Q plus R P, this has a unique solution, and this Q plus R P can be replaced by Q P star. So, this also falls in some of the basic identity of regular expression. Okay. Now, if this is the general statement given by ARDEN'S theorem, and this means what, whenever we are trying to convert any kind of finite automata to a regular expression, this particular expression will help you a lot in order to optimize or in order to give a optimal solution. Okay. Now, let me take back to the next slide and let us go with some of the basic identities which you should know it. First one is phi plus r is equals to phi. Now, okay, fine. Now, for the timing you should understand and you remember one more thing is that this phi is nothing but 0 and this epsilon is nothing but 1. Think of it like this, okay, phi as 0 and epsilon as 1. So, if we look into this, r is nothing but here as a regular expression. Okay, here r is a simple regular expression. Now, this r plus 0 means what? It will always give r. Regular expression plus 0 will always give r. If I say r plus epsilon, then that will be like counting as 1. So, I will not write that expression, that will put as an expression. We cannot solve it, we cannot optimize that particular part. Okay. Next comes phi dot r, means 0 dot r or 0 concatenated with r or r concatenated with 0, then it will always result as 0 or phi. Got it? Next comes 1, that means epsilon multiplied with r, that concatenate with r, or r concatenate with epsilon will always give you r dot 1 r. Next, epsilon to the power clean closure will always give you epsilon only. 1 to the power something, whatever you take, it will always give you 1, and phi to the power clean closure will give you epsilon. In what case? Phi to the power 0 to the power 0 will give you 1, that is one case. So, this is a particular expression identity that you need to remember. Next, r plus r, regular expression plus regular expression will give you r only. Okay. Then r asterisk r clean closure dot r clean closure will give you r clean closure only. Okay, because it is an infinite clean closure gives 0 to infinite terms. Okay. Then r dot r star is equals to r star dot r is equals to r plus. I think we know this expression since the previous video, in the initial videos, right. A to the power star means what? A to the power plus, a to the power plus means what? We have seen in the general expressions in the primitive operators, special operators, a to the power plus means what? A dot a to the power clean closure. Why? Because a clean closure starts from 0, 1, 2, 3 up till infinity, and plus starts from 1, 2, 3 and it will go to infinity. Got it? So, this is all about your basic expressions, and one more expression is there, r to the power clean closure whole to the power clean closure will always give you r to the power clean closure. Okay. So, total how many? 1, 2, 3, 4, 5, 6, 7, 8. 8 basic identities we are having. No, we are having more basic identities. Let me check in the next expression, next slide. The next slide says this is 9th, 10th, 11th, 12th and 13. Total 13 basic identities you need to memorize or need to understand. Okay. If you have understand phi equals to 0, epsilon equals to 1, then some or the other you will be able to relate this concept. Now comes over here, this basic identity you have used in the previous video lecture, where we have done finite automata to regular expression by using ARDEN'S theorem, correct. Epsilon plus r dot r clean closure is equals to r clean closure, or we can also say that epsilon plus r dot r clean closure is equals to r clean closure. Okay. So, this is the optimal solution for it. Next comes p dot q whole to the power star dot p we can also write down like this, that p dot p whole to the power q whole to the power clean closure. Okay. It is just like commutative one. Okay. Next 11th is a very important property. 11th is a very important property which is being used. P plus q whole to the power clean closure equals to p clean closure dot q clean closure whole to the power clean closure equals to p clean closure plus q clean closure whole to the power clean closure. Now, these particular expressions can be utilized in anywhere. I will show you with an example in the upcoming session, where you will be able to understand this expression utilization. Okay. Next, p plus q whole to the power r is equals to p r plus q r. So, this is the general explanation. Okay. Next, 13th one is already been done, that is nothing but the ARDEN'S theorem. So, this is also an important expression. So, overall if you can go with these basic identities, I would rather say this one and this one is an important one, and from the previous 8 identities we can say this one, this was an important one and this one is an important one. Okay. So, overall 5 to 6 identities you should like have a very solid grasp, so that while you are discussing any kind of finite automata to regular expression by using ARDEN'S theorem, or if you are proving any kind of expressions by using ARDEN'S theorem, this will help you. Okay. So, I hope you have understood all the 13 identities. Now, let us go with some of the examples. Now, the first example says you have to prove this particular expression equals to this expression. Okay. So, in the general way, let us take the left hand side part. Now, in this particular type of expressions, you try to find out some of the similarities, okay, and take that particular similarity expression as a particular you can say any expression name, say suppose r, p, q, anything, okay, and that will help you out in order to minimize the expression in some way or the other. Okay. Now, if you can look into this expression, I can see that this particular term, this particular expression, that is 1 plus 0 0 to the power star 1 and this one is somewhat similar, okay, and here this one, okay, and this one are similar, correct. But along with this similarity, you should also check that in the right hand side what is the final one. See, one expression is the one which is not changing, okay, that means this one, this particular expression is not at all changing, correct. So, I need to I no need to do anything with this particular expression, rather go with this particular concept. Okay. So, let me erase these things. Now, if you look into this, let me take the left hand side part. Okay. If I do something like this, that if I take this entirely, okay, and 1 plus 0 0 to the power star 1. Okay. Now, can I play with something with this? Okay. What I can do is this, I can take 1 as a common, I am just doing only this expression part. Okay. If I take 1 as a common, then it will be epsilon plus 0 0 to the power star. So, something it will help you, correct, epsilon plus 0 0 to the power star. So, I think if you can go back to the previous identities, this one 9th identity, it says that epsilon plus r to the power star will give you r star only, correct. So, using this identity I can write down like this, epsilon plus r to the power star will give you r star. So, 1 0 to the power star. So, that means this expression can be written in this particular form. So, I have simplified this expression, clear, got it. So, that means what I can do in the left hand side part, now I will take the entire expression, and this entire expression what I will do, first of all, besides going with the solution of it, I will try to take this expression as a whole 1 plus 0 0 star 1 as a common. If I take a common, then it will be epsilon, because epsilon x is a 1, correct, plus this has been taken out, then this will be 0 plus 1 0 whole to the power star 1, then asterisk, then 1 plus 0 plus 1 0 star 1. Okay. Now, I got this solution for this expression, what is that, 1 0 star, correct. And if you look into this particular concept, some of the other, in the right hand side I got this part, I just need to take this particular concept, right. So, this is nothing but what? This is nothing but epsilon plus r star r. So, r star r means what? R star only, and what I have taken r I have taken as this one. So, that means it will be 1 0 star, then it will be 0 plus 1 0 whole to the power star 1 whole to the power star, and this is nothing but what? Your right hand side. I hope it is clear to everyone. Okay. So, this is what I got the right hand side. Now, the entire steps by step properly I have mentioned over here. You can get back the entire context. Okay. Now, coming to the next expression, next question. The next question says somewhat a little bit a different way, but some of the other you will be able to do it. It says that prove that the regular expression r is equals to this one, okay, also describes the same set of strings. Same set of strings. Okay. Now, we are talking about not a particular alphabet, we are talking about string. If you look into the string, we are having 1 as a common string, correct, and 0 1 1 as a common string, correct. So, I will having 1 and 0 1 1. Some or the other I need a final expression which comprises of only this one after simplifying. Okay. So, this is the general approach of this question. Okay. Now, if I design this particular question in a proper way, I will get the solution like this. See, the solution says that the expression will be in this form. I have understood the basic identities, some or the other I will be able to analyze this question, correct. This 1 whole star, then 0 1 1 whole to the power star can be taken as a simple expression as p. So, this expression will act as epsilon plus p star is nothing but p star only according to the basic identity that we have seen, identity number 9. Okay. Then I got what? R is equals to p star, that is nothing but this expression, correct. Now, in this expression, if I take 1 as m and I take this 0 1 1 as n, I think the same one I have taken, no, 0 1 1 I have taken here as q, okay, fine, no issue. So, that means m star q star whole to the power star. If you remember basic identity number this one 11, then it says that m star p star q star whole to the power star we can write like this, p plus q whole to the power star. So, that means I can write like this, that m star q star whole to the power star I can write like this, and this is nothing but what? 1 star plus 0 0 1 1, okay, this is not 1 star, 1 plus 0 1 1 whole to the power star, and this is nothing but what? I have got a simplified expression which comprises or which describes the same set of strings which are nothing but 1 and 0 1 1. So, this is the general solution of this question. Okay. Now, last few topics I am left out with this particular video. There is nothing but the properties of some of the regular expressions or regular sets. Okay. These properties we have discussed in the previous videos, where we have discussed about the properties of finite automata, where we have seen the closure properties of finite automata, right. Here we will try to look into the properties of regular sets. The first property says that union of two regular set is always a regular. Union of two regular set is always a regular. Okay. The same explanation or proof I have taken by using an explanation of particular languages. So, I have taken two languages, this is one language and this is another language. Okay. The first language, how I got it? With the help of a regular expression, this one a, and in this bracket a whole to the power clean closure, and one more regular expression I have taken, I have omit this a and I have taken only a whole to the power clean closure, got it. And if you elaborate this particular regular expression in the languages, and if you take the union of these two languages, you will get the same expression again, or you will get the same language language again. So, that means we can say that this particular this particular regular sets, union of two regular set will always give you a regular concept, regular language or regular expression, because regular means what? Regular expression in the form of representation, regular language in the form of a language term, regular grammar in the form of a generator part. So, all are having different concept, but the main rule is the regular. Okay. So, the first point, I think it is clear to everyone that if union of two regular will always give you a regular. Similarly, if you take intersection of two regular, if you take definitely if you are taking two regular sets, and if there are commonalities between those two regular sets, and if you merge or if you find the intersection one, definitely you will be getting an regular sets only. Okay. So, that is the second property of it. Intersection of two regular sets is always a regular. The proof is somewhat similar to the previous one. I have taken two regular expression, one of the form of a to the power clean closure, and another form of a whole to the power clean closure. If I take into a language form, the language will explain in this format, and language 2 will give you this one. Why epsilon comes? Because asterisk value starts from 0, and if it is 0, then the first string will be your epsilon. Okay. So, if you take the commonalities 1, you will get a and followed by a whole to the power clean closure, which is nothing but what? A regular expression only. Okay. Next comes complement of complement will also give you a regular concept. I think this particular concept I have discussed. If we talk about a language which is length is even, okay, length is even means what? I will be getting 0, 2, 4, 6, correct. If I take the complement of it, if I take the complement of this language, I will get what? 1, 3, 5, 7, 9 and so on, and this is nothing but what? Length is equals to odd, and this is also what? Regular. Therefore, I can say that complement of a regular will always give you a regular. Correct. So, this is what about property number 3. Now, come back to property number 4, which is nothing but idempotent law, and the idempotent law, what it says that if idempotent law, actually I have done in the basic identity part also. I will get back to that, I will show it to you. If you look into these identities, you can pause the video and you can think of it, which is the one which is like having the idempotent law, this property, correct. So, the same question, the property number 5 is nothing but this idempotent law. That means, the expression, if you do the union with itself, will give you the same expression, correct. Next comes, the next law comes is left distributive law. Left distributive law says that if you are having an expression of this form L, and I am having an expression of say suppose m plus n, okay, and if you try to do a merging of it or union of it, then what I will get? I will get L m plus L n. So, this is what I am trying to do from the left hand side, okay, and the similar way vice versa, if you do from the right hand side, then that law will be your right distributive law. Okay. I have tried to now take m plus n over in this expression, and then union I am doing ln, then I will be getting what? M L plus N L. Okay. So, these are the different types of laws that we are having: right distributive, left distributive, idempotent. Then we are having some of the properties where we can directly say that this is closed under, one is union, intersection, complement. Okay. So, these are some of the basic properties of a regular sets. So, I think in this particular video session, I have tried to explain to you that what are the basic identities involved, just a summary of what we have learned till now. Okay. And I think total I have taught you 13 basic identities, okay, out of which 5 are very important, which I have marked in the video lectures. Then one more is that what we have learned, that how to use these identities. Okay, this concept we have seen, and for this I have done 2 examples in order to let you know, but you need to practice a lot so that you can grasp all the identities in a smoother way. Okay. Then we have seen some of the properties of regular sets or regular expressions. Okay. So, this is all about your today's video that we have learned, and I would suggest that please go through these basic identities in a proper way, because these are the identities which will help you in order to convert any finite automata to a regular expression by using ARDEN'S theorem. Okay. And if you know like some of the basic identities, then definitely you will be able to understand how to solve or how to simplify those identities. Got it? So, for that you need to practice few of the examples, and then finally, we have seen some of the properties which you will come across with every unit, okay, because every unit comprises of different machines, okay, and for all the machines we are having different languages, definitely we are having different properties for them. Okay. Now, overall, if I go back to the previous slide, here I have done it. I am just taking the part where I can show it to you that what you need to learn in from unit number 2. In unit number 2, first you please concentrate on the regular expression part. Okay. In the regular expression, you just try to focus on what are the operators being used, how to what are the primitive operators are used, what are the special operators are used, what are the primitive expressions are used. Then you can check that regular expression to finite automata. Okay. So, there I have shown you some of the basic expressions from where you can convert to a finite automata, and then I have discussed few of the examples with the help of which you were able to convert to a finite automata. Got it? Number 3rd, okay, this hierarchy you should know it, so that it will be helpful for you to analyze. Then next you have seen finite automata to regular expression, and for this you will be coming across with two concepts. One is your ARDEN'S theorem that you have already seen, okay, and one more is there, that is known as your state elimination method, which we will be discussing in the upcoming video. Okay. So, these are the two methodology with the help of which you can convert a finite automata to regular expression. Then we have seen one more concept, that is regular expression to epsilon NFA. Okay. For epsilon NFA, I have told you that we will be using the concept of Thomson's algorithm, okay, Yamada Norton Thomson's algorithm. So, with the help of which you have tried to convert an regular expression to epsilon NFA, correct. And then we have seen these concept, and then we have seen some of the basic identities, okay, and you need to follow these identities in a proper way, plus examples, or you can say proofs of this. Okay. Then we will be looking some of the properties, okay, and these properties will comprises of closure properties as well as decision properties. Okay. If you can understand these two properties, and these properties are applicable for all regular languages. If you know regular languages, regular expression, and then finite automata, everything will be like similar. Okay. And finally, we need to understand how to identify that a language is regular or not. So, this is a very important concept if you are talking for any competitive exam point of view. Okay. If you are talking for your exam point of view also, right now you are doing MCQ exams. So, there also this particular concept is very important, which we will be discussing in the upcoming video. And last, we will discuss pumping lemma. So, overall these 8 topics are enough for you to understand the concept of regular expression. Okay. So, this is all about your today's video. We will come across with one more interesting topic. I think we are left out with this particular concept, pumping lemma, then 7th point, okay, and properties we are done, and yeah, we are done with almost all the concepts. Yeah, one more topic is there, state elimination. So, in the next video we will come across with these 3 topics in a proper example wise. Okay. So, thank you for watching this video. Keep tuned. Let us meet in the next video. Thank you.